Okay, so now we move to the measurement matrix design. First, we remember that we have two main elements to make sure to obey in order to be able to solve this problem. First, I have to understand the sparsity. We have to acquire a sparse signal. We already studied that. And now we want to know how to design a properly a measurement matrix. Okay, so we talk here about the coherence, which is one of the main properties if we want to check whether my matrix is a good candidate to my compressed sensing problem or not. Okay, so the analysis of recovery algorithms, it usually involves a quantity that measures the suitability of the measurement matrix, which is here, we call it the coherence. And this coherence, the smaller it is, then the smaller samples or measurements we would require. So I can actually go into like reducing the size of my output compressed signal to a maximum if I'm actually having a very, very good coherence. So by definition, we would have a matrix A, our measurement matrix A, with L2 normalized columns that are A1 until AN, where it's actually like we are here normalized. So any L2 norm of the columns would be equal to 1. And the coherence mu A of the matrix A is nothing than the maximum value amongst the absolute value of the inner product between like column wise uh, in our matrix. So, and this of course like a random process. I'm trying like okay random, but I'm having this complete calculation amongst all the columns of my matrix. You could see it here. And all subsets that consist of k columns, taken randomly from A, are actually nearly orthogonal. So if uh, what I'm having is are actually nearly orthogonal, then we can say that our matrix is good for compressed sensing. So what could be the value of the coherence? It actually varies between 0 and 1, its absolute value between 0 and 1. So if we have 0 value, then we have the least coherence. And if our mu is 1, then we have a full coherence, particularly for full rank matrices, which are like really good matrices that do not like destroy the quality of the signal. Everything is preserved. These they satisfy the following inequality, and of course, n is the signal size, and m is the measurement size, and 1 is of course the maximum that I can actually get. So this is a simple and useful measure of the quality of a measurement matrix. It seems like easy. Okay, what should we do? We have to calculate column wise the inner product between each of them, and the maximum value would tell me whether my matrix is good or not. Okay, easy peasy. We understood that. But let's think about this from a programming point of view. This actually has a limitation of the performance analysis of the recovery algorithm to small sparsity level due to its lower bound. So this could actually work, of course, but preferably only when you have a tiny, tiny type of signals to treat. So the solution here would be what Professor Candace has proposed, which is called the restricted isometry property. So this turns out to be a very useful, like a way to study the robustness of compressed sensing. It's one of the most used tools to certify whether a measurement matrix is good or not for my compress sensing problem. It measures the orthogonality of all subsets of k columns taken from the measurement matrix. I explain myself. So here, how it works is that we are checking uh, how close or how near the like columns of my matrix could be close to orthogonal. So I will be picking at random these columns, and I will be testing for orthogonality, of course, using inner products, and to check um, whether this is good or not. And it provides, I mean, in this procedure provides a final measure of the quality of my measurement matrix that overcomes the limitation that we have seen before. So here, when we say that if we have the RIP, if the RIP property is holding, then all the k subsets that you pick from your measurement matrix should be nearly orthogonal. They cannot be perfectly orthogonal, but they have to be close, or like better speaking, we say nearly orthogonal. And this, and in this way, we can ensure the success of the sparse recovery algorithm. So, how to verify this, and like a little bit of mathematical representations here would be, we want to calculate what we call the kth restricted isometry constant that we define by delta k of a matrix A. Our measurement matrix A is actually the smallest delta k in 0 and 1, such that for any k sparse signal x we would have the following inequality. If this inequality holds, then we can say that A satisfies the restricted isometry property of order K. So we said that this delta K could be between 0 and 1. So if my RIP gets closer to 1, um, then we are getting a little bit away from obeying the RIP, and maybe we are losing uh, the property or the ability to say that we have a compressed sensing problem. Here, there is a difficulty in constructing deterministic matrices with the RIP until today. So, okay, we say that I can pick whatever matrix that would obey this specific inequality here, and then the job is done. But from a programming point of view, that is actually a really tough um, uh, operation until today. So it's actually a very um, a very bad idea if you want to design your matrix in a deterministic fashion by following the way of obeying the restricted isometry property. So here we have um, like somehow like somebody feels a little bit struck. Okay, you tell me it has to obey the rib, but at the same time you tell me that it's also a bad idea to design the matrix in a way that should obey the rib. But don't go far, we'll get there soon. There are also other properties, like for some cases this rip is not valid, so there are some ways to substitute it. They're not as strict, let's say, as the rip, but remain a good candidate. For example, the null space property here could be a very good way to be used when when we deal with finite field values, because there we don't have um, like the norms, inner products and stuff, but null space uh, uh, is actually concerned about the kernel of a vector space. But uh, let's keep in mind that we will see this a little bit in detail. Sorry, in the next lecture. There is also restricted eigenvalue property and others that you do not have to bother knowing about. So back to our RIP, the the question that has always remained, we need a more practical solution. But here there is a very nice surprise for everybody, is that if you pick entries of your matrix A uh, from a random Gaussian distribution, Bernoulli, sub-Gaussian, or a random, not a random Fourier ensemble, then nicely the RIP is preserved with a high probability. So the concern regarding satisfying all the properties we have mentioned before could be discarded, and each time you want to have a compress sensing problem, then simply pick a Gaussian matrix, for example, or Bernoulli, and the choice could be done based on what you or what you want or what the application requires better. For example, if you use Bernoulli coefficients, then you have less storage problem because like Bernoulli could be zeros and ones or minus and pluses. Zeros and one require less storage requirements and less computations compared to Gaussian. Gaussian could be a little bit lossy if we like do the compression over uh, um, a multi-hop network where I have to do recompress like compression over and over again, and we will be lost in the like in these errors due to floating numbers multiplication. Okay, so now um, we show some basic reconstruction algorithms. Remember, we have seen first this L0 minimization, which is a combinatorial problem that is non-convex, that is not advised to use. And then we've seen a little bit of improvement with the basis pursuit, which is a linear program using L1 minimization. And then like when people started paying attention to compressed sensing, it was like an explosive number of algorithms that have spawned at the time, and until now we see many new papers appearing with new promising algorithms. So in general, you could not pick these reconstruction algorithms uh, like there is no final decision. Let's say you have to really pick it based on the application that you are having, the signal type, the choice, the signal type, your topology whatsoever, and also at the receiver side, how much computation your receiver could do to reconstruct, and so on. So as it is hard to discern the number of these algorithms that are available in the literature, there have been some major classifications, amongst which we name a few that are really important. We have the convex relaxation, what we have seen before, the basis pursuit. There is also another one, basis pursuit denoising, least absolute shrinkage and selection operator lasso, which is a very famous and old algorithm that is also a very good um, algorithm, like you could see appearing a lot in the literature. And there is also another class called the greedy pursuits that contains the orthogonal matching pursuit, which I personally favor a lot, and I find it really easy for whatever work I do. I just use the OMP. Also, a little bit further, we will show a simple example about it. There is also the compressive sampling, match and pursuit, and there are other algorithms, algorithm class called thresholding based algorithm, like iterative hard thresholding or soft thresholding, hard thresholding pursuit, and so on and so forth. And finally, like last but not least, message passing algorithms, for example, like belief propagation that is widely used with LDPC codes or approximate matching pursuit. So, could be a good hint for choosing the right algorithm, basically the complexity and the number of measurements. So, as we mentioned before, so you have to check your system specifications, for example, your tolerance to errors, your recovery speed, and the number of your available measurements, etc. And here I picked like most used algorithms in the literature. So we have this basis pursuit with a complexity of ON cubic, and it requires an average number or approximately k log n number of measurements. We have the subspace pursuit with a complexity of OKMN, um, also with the uh, this number of measurements, also OMP and the um COSAMP, which has the least complexity here. Yeah, and you can easily remember that the basis pursuit is the one with the highest complexity here. Okay, so now we move finally to um, this nice example that shows how the orthogonal matching pursuit work. So here we have a signal that is sparse. Here X is composed with these elements, and we have this random measurement matrix of dimension 2 by 3, and here it's components. Of course, we can now write the compressed sensing problem as y equals ax, and by multiplying x and a, of course, I remind you it's not a simple multiplication here. We are doing a dot product. We obtain y with these values. So now the task is given y, this one, and a, we propose to recover x. So we pretend that this x is something that we don't know, but we actually would like to find using a and y. Okay, so before going further, we try to like break the problem into some pieces. So first we name the columns of A, also called atoms. It's preferred to use the word atoms as follows. We break them into B1, B2, and B3, and then we suppose that our signal X could be written as like alpha, beta, gamma. It has three components, so we just do it like that. And a nice analytical expression or a linear combination writing would give me y equals ax, which is alpha times beta 1, alpha times b1, beta times b2, and gamma times b3. And here we can see how my y could actually be. Okay, so we start Like how this OMP work? We start by finding the atom that has the strongest influence on Y, then find the second one using what we call the residual that we will see a little bit later, and then continue until the residual achieves a certain threshold. Okay, so in a simplified way, um, the OMP algorithm could be seen in like 4 steps. First of all, like initialization, we would like to find the atom which has the biggest inner product with Y. So we just go. Of course, here I apologize. It should be an absolute value of the max inner product here. And based on what we obtain, we calculate the residue using the following formula, and then we find the atom which has the biggest inner product with Ri. So here in the beginning we started with Y. This is like it's in our initialization. Then we substitute the Y with whatever Ri that I had, and then I will be iteratively go in the loop of 2 and 3. I will have to repeat until the residue achieves a certain threshold. So here in our example, we calculated these inner products. We could notice that the absolute value of the first one is, let's say, a winner. So we choose it as the atom of the first step. And then next, we calculate this residue using the following um, formula here: y minus b times the inner product between b and y, and we get a certain a value for R1. Then we count, like uh, next step, we have to count the inner product of the residue R1 to the remaining atoms, which are B2 and B3. And here you could notice that B2 has the strongest influence because the inner product was larger. Sorry, the absolute value of the inner product was larger than the other one. And next we calculate again this residue using the R1 and B2 and so on. And finally, from the new residue that we obtained, we calculate the last dot product between R2 and B3, and we obtain this specific value. Okay, so the results are actually sorted based on the strongest order as follows. So in this example, we had B1, like B1 was the strongest, B2, and then B3. In another example, might be B3 is the strongest, or well, the first one that has been used, so it has to be really the first one, and so on. So here, uh, we sort them based on this strongest order with the respective influence from the inner product. So these are the values we calculated. This we got when we multiplied, we got the inner product between B1 and Y. Here, uh, um, I think R1 and B2, and here R2 and B3. So as a result, our reconstructed signal X is the following. So if we compare with the original one, we see the error here. We have like not matching, but hopefully it's not that bad. The second element is perfectly restored, and the last one also slightly different. Um, to my point of view, this is actually a very good way. Like you had only two equations to solve three unknown problem. you could reconstruct or you could retrieve one of the elements perfectly, and it is perfectly put in its position, and the less sorry, the rest of the two elements are approximately close. Um, but this is just an example using three elements. So if we remember that compress sensing works usually on a high dimensional signals, which have hundreds of elements uh, to represent. Um, and in that case, like perfect reconstruction could be visible. But this doesn't make this example actually that bad, and it might be a little bit tricky to recreate the same example if you have this really minimal number of elements. Okay, so that was it for the lecture for today. There is gonna be the follow up with a next lecture. I hope more information will be brought, and I really hope that you could get the very basic idea of compressed sensing here. Mm, Unfortunately, we are not given a lot of time to teach compressed sensing, but I tried to make it as simple, as friendly as possible. And if you have questions, please do not hesitate to contact me via email, or if you notice any mistakes or uh, whatsoever, because we are stressed with this kind of recording, please also like friendly drop me a line so I can adjust or edit my slides. Thank you very much.